The universe should not exist. Every physicist alive knows this. And yet, here you are, breathing, thinking, watching, inside a cosmos that had every reason to never happen at all. That's not poetry. That's not philosophy. That's mathematics. When physicists began calculating the conditions required for a universe like ours to exist, not a universe with life, not a universe with planets or stars, but simply a universe that doesn't instantly collapse or explode into nothing, they found something that stopped them cold. The numbers that govern reality, the fundamental constants baked into the fabric of existence itself, are calibrated with a precision so extreme, so unreasonably exact, that the word coincidence starts to feel almost offensive. And here's what nobody tells you. The scientists who discovered this didn't want to find it, because what they found wasn't a gap in knowledge. It wasn't a mystery waiting for a better theory. What they found was a pattern, a signature, embedded in the deepest layer of physical reality. And that pattern looks less like an accident and more like an answer to a question nobody had the courage to ask. By the end of this video, one thing you currently believe is settled science will no longer feel settled, not because someone is selling you a theory, but because the numbers themselves are going to force that feeling out of you. So let's begin with the most uncomfortable fact in all of modern physics. There are constants, numbers that show up in the equations governing the universe that have no known reason to be the value they are. They simply are what they are. The gravitational constant, the speed of light, the mass of the electron, the strength of the electromagnetic force. These numbers didn't emerge from a deeper equation. They weren't calculated. They were measured. And what physicists discovered as they mapped the consequences of each one is that almost any change, no matter how small, produces a universe where nothing meaningful can exist. Change the gravitational constant by 1 part in 10 to the power of 60, and stars never form. There is no hydrogen fusion, no stellar nurseries, no periodic table being forged inside collapsing giants, just a cold, diffuse fog spreading forever into nothing. Adjust the electromagnetic force by a few %, and atoms cannot hold themselves together. Chemistry collapses before it begins. No molecules, no DNA, no complexity of any kind, ever. Alter the ratio between the mass of the proton and the mass of the electron by less than 0.5%, and every star in the universe either burns out in seconds or never ignites at all. These aren't edge cases. These aren't extreme scenarios requiring dramatic changes. These are catastrophic failures triggered by adjustments so tiny that calling them small would itself be an understatement. The physicist Fred Hoyle, a man who spent his career as a committed atheist, stumbled onto something similar when he calculated the nuclear resonance levels of carbon-12. Carbon is the scaffolding of biological life. For it to be forged inside stars, the energy levels of carbon and oxygen nuclei have to align within an impossibly narrow window. If they were off by even a fraction, carbon wouldn't accumulate in stars. It would be bypassed entirely. And all of biology, everything that has ever lived on this planet or any other, would be chemically impossible. When Hoyle ran the numbers, he found that they aligned. Precisely. Exactly. The universe had threaded a needle that had no business being threaded. And Fred Hoyle, the atheist, wrote that nothing had shaken his atheism as profoundly as that calculation. He didn't convert, but he admitted publicly that it looked like something had monkeyed with physics. That phrase haunts the field to this day. Because here is the question that physicists quietly pass around but rarely publish. If the universe had no designer, why does it look exactly like it did? Not approximately, not loosely, exactly. And here is where the discomfort deepens into something stranger, something that makes this more than a question about God or religion or belief. This is a question about the tools of science themselves, because science, at its core, explains how things work. It maps mechanisms. It traces causes to effects. It is extraordinarily good at answering the question of how. But the deeper you follow those mechanisms, the further back you push the chain of causes, the more you find something science was never designed to confront. Not a gap, not an absence of information, a presence, a structure, a set of numbers that sit at the foundation of all physical law that have no mechanistic explanation, that could have been anything, and that happened to be precisely, almost surgically, the values required for a universe like this one to exist. Science explains how the universe runs, but something set the parameters before it started running, and that something is exactly what science refuses to name. 3 questions are now open, and none of them have clean answers. What are the actual odds that those constants landed where they did by chance? And do those odds even mean anything in a universe where probability itself had to be constructed? Why do the physicists who understand this most deeply speak about it in private with a kind of unease they rarely put into papers? And what does the word designed even mean when there may be no designer? When the alternative explanations are so strange, they make a creator sound simple by comparison. Those questions stay open. They're supposed to. Because the unsettling thing about the universe is not that it's mysterious, it's that the closer you look, the more it resembles something deliberate, and you haven't even seen the evidence yet. Martin Rees is not a theologian. He is the Astronomer Royal of Great Britain, one of the most decorated cosmologists alive, and a man who has spent his entire career committed to a purely naturalistic understanding of the cosmos. So when he wrote that the existence of the universe as we know it depends on 6 numbers, and that if any one of them were even fractionally different, nothing would exist, he wasn't making a spiritual argument. He was making a mathematical one. And mathematics, unlike faith, does not care whether the answer is comfortable. 6 numbers. That's all that stands between existence and absolute nothing. Not 6 theories. Not 6 philosophical positions. 6 specific, measurable, dimensionless values embedded in the laws of physics. Values that govern everything from the architecture of atoms to the large-scale structure of the cosmos itself. Change any single one, even microscopically, and the chain reaction of consequences is not gradual. It is not recoverable. It is immediate, total, and permanent. Let's be precise about what that means. Because precision is exactly what makes this so disturbing. The first number is called epsilon. It governs the efficiency of nuclear fusion, specifically how much mass is converted into energy when hydrogen nuclei fuse inside stars. The value of epsilon is 0.007, not 0.06, not 0.08, 0.007. If that number were 0.006, protons would never fuse. Hydrogen would be the only element in the universe. Stars would burn for a moment and die without producing a single atom of helium, carbon, oxygen, or any of the heavier elements that make chemistry possible. You would not exist. Life would not exist. The concept of a molecule would be a mathematical curiosity in a universe of isolated, inert hydrogen gas, drifting forever in a cold, dark expanse that never once organized into anything. If epsilon were 0.008, the opposite catastrophe unfolds. Fusion would be so efficient that hydrogen would be consumed almost instantly after the Big Bang. Stars would burn out in geological eye blinks. There would be no long, stable stellar lifetimes, no slowly warming planets, no billions of years of consistent energy output giving biology time to unfold its extraordinary complexity. The universe would burn brilliant and fast, and then collapse into a graveyard of dead stellar remnants long before the first amino acid could assemble itself. The number is 0.007, balanced on the edge of two different kinds of death, like a coin standing perfectly upright between two cliffs. And nobody knows why. The second number is N, the ratio of the electromagnetic force to the force of gravity. Written out, N is approximately 10 to the power of 36. That is a 1 followed by 36 zeros. This number looks enormous, but its enormity is not an accident. It is a requirement. Gravity is extraordinarily weak compared to electromagnetism. Absurdly, almost insultingly weak. A small magnet can lift a paperclip against the gravitational pull of an entire planet. And that weakness is the reason the universe has had time to become interesting. If N were even slightly smaller, if gravity were even fractionally stronger relative to electromagnetism, stars would form faster and burn hotter and collapse sooner. In a universe where N was a mere 10 to the power of 30, stars would have lifetimes measured in thousands of years rather than billions. Planets would barely have time to form before their host star exploded. Life, which requires geological timescales of stability, would never find its footing. The ratio is what it is, calibrated to allow for a universe with a long, slow, productive middle age. A universe with enough time for something like us to appear and notice it. The third number is omega, the density of matter in the universe relative to the critical threshold that determines whether it expands forever or eventually collapses back in on itself. The value of omega had to be extraordinarily close to 1 in the early moments of the cosmos. Physicists estimate that 1 second after the Big Bang, omega was equal to 1 to within 1 part in 1,000 trillion. Let that sit for a moment. 1 part in 1,000 trillion. If omega had been even slightly higher, if there had been fractionally more matter, gravity would have won. The expansion of the early universe would have slowed, reversed, and collapsed everything back into an infinitely hot point long before a single star had time to form. The universe would have ended before it began. If omega had been fractionally lower, the universe would have expanded too fast. Matter would have dispersed before gravity had any chance to pull it into galaxies, stars, or anything else. The cosmos would be a thin, cold, featureless gas, perfectly uniform, perfectly empty of structure, perfectly dead. 1 part in 1,000 trillion. The most precisely balanced number you have ever encountered. And it was said in the first second of existence. The 4th number is lambda, the cosmological constant, also called dark energy. This is the value that governs the rate at which the universe is accelerating in its expansion. Lambda is so small that for decades, most physicists assumed it was exactly 0. When it was discovered in 1998 to be non-zero, it triggered what many cosmologists now quietly describe as the deepest crisis in theoretical physics. Because the value of lambda, as calculated from quantum field theory, should be enormous. The theoretical prediction and the observed measurement disagree by a factor of 10 to the power of 120. That is not a rounding error. That is the largest discrepancy between theory and observation in the entire history of science. If lambda matched its theoretical prediction, if dark energy were as strong as quantum mechanics suggests it should be, the universe would have been torn apart almost instantly after the Big Bang. Expansion would have been so violent and so rapid that matter could never have clumped into galaxies or stars or anything at all. Reality would have shredded itself before it had a chance to build anything. Instead, lambda is almost nothing. Just barely non-zero. Just enough to cause a slow, gentle acceleration observed only at cosmic scales. Just enough to be real without being catastrophic. Nobody knows why. The most sophisticated theoretical framework in physics predicts a number that is off by 120 orders of magnitude, and the universe simply ignores that prediction and does something almost impossibly restrained instead. Physicists call this the cosmological constant problem. What they mean is, we have no idea why the universe is still here. The 5th number is Q. The amplitude of the irregularities imprinted on the early universe. The universe that emerged from the Big Bang was not perfectly smooth. There were slight variations in density, ripples in the fabric of the early cosmos, and Q measures how large those variations were. The value is approximately 1 part in 100,000. This number is the reason structure exists at all. Those tiny density variations were the seeds of everything, the places where gravity pulled matter slightly harder, creating the first clumps that grew into galaxies and galaxy clusters and the vast web of cosmic architecture that fills the observable universe. If Q were smaller, those seeds would have been too faint. Gravity would have smoothed them away before they could grow. The universe would be a perfectly uniform gas, and no star or galaxy would ever have formed. But if Q were larger, the opposite problem, density variations would have been so dramatic that matter would have collapsed into supermassive black holes before stars could form. The universe would be a landscape of crushing gravitational singularities, not luminous galaxies. No stable solar systems. No chemistry. Nothing. 1 part in 100,000. The universe is littered with structure, but not too much of it. Just enough of the right kind, arranged at precisely the right scale, seeded by a number no theoretical framework has yet explained from first principles. The 6th number is D, the number of spatial dimensions. 3, not 2, not 4. 3. This may seem obvious, because you live inside it. But it isn't obvious at all. Stable planetary orbits only exist in 3 dimensions. In 4 spatial dimensions, the gravitational law changes in a way that makes closed orbits impossible. Planets spiral inward and are consumed by their stars. In 2 dimensions, sufficient complexity for something like a nervous system cannot arise. 3 spatial dimensions are not just the ones we happen to have. They are the only configuration in which a universe can contain stable structures and complex systems simultaneously. And there is no known physical law that requires the universe to have exactly 3 of them. 6 numbers, all sitting in extraordinary positions between 2 different versions of catastrophe. All measurable. All real, all agreed upon by physicists across every school of thought and every theoretical framework. The fine-tuning is not in dispute. What physicists violently disagree about is what it means, and that disagreement is itself a kind of evidence, because it reveals how deeply uncomfortable the conclusion is when you let the numbers speak for themselves. These constants have been known for half a century. In 50 years, no theoretical framework has explained why they have the values they do. No deeper equation has been found from which they fall out naturally. No principle has been identified that selects these numbers over any other. They simply are what they are, precise to dozens of decimal places, calibrated to a standard of accuracy that no human engineer has ever approached in any design system, and they arrived that way at the beginning of time. 6 numbers, all perfect, all unexplained. And here's the part nobody talks about in the papers, in the press releases. In the careful public statements of careful scientific institutions, physicists have known about this for 50 years, and there is still no agreed upon answer. Not a provisional one. Not a leading candidate. No consensus. No convergence. Just competing frameworks, each with fatal problems, circling a question that refuses to be dissolved. That silence is the most terrifying thing in modern science. And we are about to walk directly into it. Science has an answer to everything we just covered. A clean, elegant, widely accepted answer that has been cited in textbooks, repeated in documentaries, and used to reassure generations of students that the fine-tuning problem is not really a problem at all. The answer has a name. It has serious scientists behind it. And it sounds, at first, completely reasonable. The problem is that the answer doesn't actually answer anything. You've probably encountered this argument before in some form and found it satisfying. Most people do. It has the texture of logic. It arrives with the confidence of settled science. And by the end of this section, you will not find it satisfying anymore, not because someone is going to argue against it emotionally, but because when you look at it closely, the structure of the argument turns out to be hollow at its core. The argument is called the anthropic principle. It goes like this. Of course, the universe appears fine-tuned for life. Of course, the constants are calibrated in a way that permits our existence. Because if they weren't, we wouldn't be here to observe them. The very fact that we are asking the question proves that the conditions necessary for asking the question were met. The universe had to be compatible with life, because only a universe compatible with life could contain observers. The apparent fine-tuning is not a mystery. It is a selection effect. We selected ourselves into a universe that could produce us, simply by existing. It sounds airtight. And for decades, it functioned as the primary intellectual shield against the unsettling implications of what physicists were finding in their equations. But here is what the anthropic principle actually does when you examine it carefully. It explains why we observe a life-permitting universe. It does not explain why a life-permitting universe exists. That distinction sounds subtle. It is not subtle. It is the entire problem. Imagine you are standing before a firing squad. 20 trained marksmen raise their rifles. The order is given. 20 shots ring out, and every single one of them misses. You are alive. You stand there, stunned, trying to understand what just happened. Now imagine someone approaches you and says, "There's nothing surprising here. If they had hit you, you wouldn't be alive to wonder about it. The fact that you're wondering about it proves you survived. Selection effect. Mystery solved. You would not find that satisfying, because the question was never whether you could be alive to wonder about it. The question is why all 20 marksmen missed. The anthropic principle addresses the first question and ignores the second entirely. It explains the precondition for asking the question while leaving the actual question completely untouched. This is not a fringe critique. This is an objection raised by serious philosophers of science, including those with no theological agenda whatsoever. The anthropic principle, in its most basic form, is logically circular. It tells you that observers exist in universes that permit observers, which is true, and which explains nothing about why such universes exist or why their constants are set the way they are. But there is a deeper problem. And this is the part that is almost never discussed in the popular explanations. For the anthropic principle to function as a genuine explanation, for it to actually dissolve the fine-tuning problem rather than simply reframe it, it requires something that is not in evidence. It requires that there are many universes. Not just our universe, with its improbably calibrated constants, but an enormous ensemble of universes, each with different values, each with different constants, filling out all the possible configurations that physics allows. If enough universes exist, the reasoning goes, then some of them will randomly land on life-permitting values, and observers will inevitably find themselves in those universes, because those are the only universes in which observers can exist. The anthropic principle, as a solution to fine-tuning, only works if the multiverse is real, not as a poetic metaphor, not as a theoretical possibility, actually real. And here is where something quietly extraordinary is happening inside physics, something that the public summary of this argument almost never mentions. The multiverse is not an established scientific fact. It is a hypothesis. It has not been observed. It cannot currently be tested. There is no direct empirical evidence for its existence. The inference toward it comes entirely from the need to make the anthropic principle function as an explanation, which means that the most popular scientific response to fine-tuning requires an unverified cosmological structure of literally infinite scale and zero direct observational confirmation. This is the move that mainstream science makes with great confidence and very little acknowledgement of what it costs. To avoid the conclusion that one universe was improbably tuned, the solution is to propose an infinite number of universes, none of which we can see, measure, or test, and then to say that in such an ensemble, a universe like ours is inevitable. The fine-tuning is dissolved by dilution. Across enough universes, anything happens eventually. But notice what has happened to the standards of evidence in that move. Physics, the discipline that demands measurement, falsifiability, reproducible observation, has responded to an uncomfortable set of numbers by invoking an infinite invisible ensemble that operates entirely outside the reach of any instrument or experiment. And then it has presented that invocation as the scientific alternative to the conclusion that something unusual is happening. Roger Penrose, one of the most rigorous mathematical physicists of the last century, has been particularly pointed about this. His objection is precise. If you are going to use a multiverse to explain why our universe has its particular properties, you still have to explain what generates the multiverse and whether the mechanism that generates it is itself fine-tuned. You have not eliminated the problem. You have moved it back one level. The universe's fine-tuning is now replaced by the fine-tuning of the multiverse generating mechanism, and you are still left asking why that mechanism has the properties it has rather than some other properties. The regress does not terminate, it just retreats. And there is something else. Something that cuts even deeper into the logic of the anthropic escape route. Even if you grant the multiverse, even if you accept, on faith, that an infinite ensemble of universes exists, and that ours is simply one of the lucky ones, the anthropic principle still cannot explain why the constants are fine-tuned to the degree they are. Because here is the critical mathematical point. In a universe-generating process that produces random constants, most life-permitting universes would not look like ours. They would be far simpler. They would contain the bare minimum necessary to produce observers. Perhaps a universe with only a thin scattering of atoms, or a universe with only a single galaxy, or a universe so minimal that it barely crosses the threshold of supporting conscious experience at all. Our universe, with its hundreds of billions of galaxies, its extraordinary chemical richness, its deep physical laws generating complexity at every scale, is not what you would expect from a random draw in a multiverse lottery. It is staggeringly more structured than it needs to be. If all you required was a universe that could produce observers, you would expect to find yourself in the most minimal observer-permitting universe possible, not in one of the most structured and elaborate ones. This argument, known in philosophy as the Boltzmann brain objection, and more broadly as the problem of typical observers, suggests that even with a multiverse, our specific universe is still wildly improbable. The anthropic principle explains why we are in a life-permitting universe. It does not explain why we are in this life-permitting universe. With this degree of complexity, this degree of structure, this degree of apparent over-engineering. So let's review what has happened. We began with fine-tuning. 6 numbers calibrated to precisions that defy ordinary probability. We introduced the main scientific response to that observation, the anthropic principle, which says the appearance of design is a selection effect rather than a genuine mystery. And we found that the anthropic principle requires the multiverse to function. that the multiverse is unobserved and currently untestable, that invoking it simply relocates the fine-tuning problem rather than solving it, and that even granting the multiverse, the specific character of our universe remains unexpectedly elaborate. The escape route is blocked. Or rather, it was never really an escape route. It was a door that when you open it leads to a room with no floor. And here is what that means for where we are in this investigation. Fine-tuning is real. The numbers are what they are. The main scientific counter-argument has been examined and found to be, at minimum, philosophically incomplete, and at maximum, a hypothesis propped up by another untestable hypothesis, stacked on the assumption that the problem goes away if you make the scale of the explanation large enough. You have no safe answer now, and the scientists who understand this most clearly know it, which is why some of them went looking for another exit, another framework, another way to dissolve the problem before it forced a conclusion that physics was not prepared to make. What they found was stranger than fine-tuning, stranger than the multiverse, stranger, arguably, than anything else in this entire conversation. And it begins with a question so simple it sounds almost childish until you realize that nobody in the entire history of science has been able to answer it. Physicists built a solution. It took decades of theoretical work, drew in some of the most brilliant minds in the history of science, and emerged from the deepest and most sophisticated frameworks modern physics has ever produced. It is called the multiverse. And the more carefully you examine it, the more it starts to look less like a solution and more like a symptom. A measure of exactly how desperate the situation became when the numbers refused to behave. To understand why the multiverse exists as a scientific idea, you have to understand the pressure that produced it. Because it did not emerge from observation. No telescope found evidence of another universe bleeding into ours. No particle accelerator detected the signature of a colliding bubble of spacetime from a neighboring cosmos. The multiverse was not discovered. It was inferred, constructed theoretically as the only available mechanism that could make the anthropic principle function as a genuine explanation rather than a circular one. If fine-tuning is to be dissolved by selection effects, there must be enough universes for selection to work on. And enough, in this context, means something that should stop you completely. Enough means infinite, not a large number, not a very large number. Infinite, an endless, boundless, unobservable ensemble of universes, each one causally sealed from every other, each one running its own physics with its own constants, filling out every possible configuration of the laws of nature across a space so vast that the word vast has ceased to carry any meaning. This is not a poetic description. This is the literal mathematical requirement of the framework. For the multiverse to solve the fine-tuning problem, it must be effectively infinite in scope. Because only across an infinite range of possible configurations does it become inevitable that some universe will land on the values we observe. And here is the thing that most science communicators will not say out loud, plainly in direct language, that claim is metaphysical, not in a dismissive sense, in a precise, technical, philosophical sense. A claim is metaphysical when it posits the existence of entities that lie permanently and in principle outside the reach of observation or empirical test. The multiverse, as required by the anthropic solution to fine-tuning, is not merely currently unobserved. It is unobservable by construction. The causal structure of space-time, as we understand it, means that other universes in the eternal inflation model, the leading multiverse framework, are separated from us by horizons we cannot cross, cannot signal across, and cannot receive any information from. They are not hiding behind a sufficiently powerful telescope. They are outside the boundary of what physics, even in principle, can access. This is the move that requires your full attention, because what happened here is extraordinary. Science, the discipline built on the principle that claims must be testable, that theories must make predictions that can be checked against observation, that the entire enterprise depends on the ability to distinguish between what is true and what merely sounds plausible, responded to an uncomfortable set of numbers by constructing an infinite invisible architecture and then presenting that architecture as the scientific alternative to a metaphysical conclusion. The infinite multiverse is offered as the rational, naturalistic answer to fine-tuning. But it is not testable. It is not falsifiable. It cannot be confirmed or refuted by any experiment or observation currently conceivable. By the standards that science applies to every other claim it makes, the multiverse does not qualify as science. It qualifies as philosophy. Specifically, it qualifies as the same category of claim it was invented to replace. To avoid one unverifiable metaphysical claim that a designer set the constants, physics constructed another unverifiable metaphysical claim that infinite universes exist and vary randomly. Neither can be proven, neither can be tested. The question of which you accept is no longer a scientific question. It is a philosophical one. It is a question about which extraordinary claim you find more credible, more parsimonious, more consistent with your prior assumptions about the nature of reality. And that is a genuinely remarkable situation for a discipline that has staked its authority on being the alternative to exactly that kind of reasoning. But the problem runs deeper than falsifiability. Because even granting the multiverse every benefit of the doubt, even accepting generously that it exists and operates as the framework describes, there are internal problems with the solution that its proponents have not resolved. And some of those problems are not minor technical difficulties. They are foundational. The first is what philosophers call the measure problem. In an infinite multiverse with infinite universes, how do you calculate the probability of any particular outcome? Probability is a ratio, the number of ways a particular result can occur divided by the total number of possible outcomes. In a finite system, that calculation is well defined. In an infinite system, it breaks down entirely. Infinity divided by infinity is not a number, it is undefined, which means that in a truly infinite multiverse, the statement a universe like ours was probable or a universe like ours was improbable becomes mathematically meaningless. You cannot calculate the odds of our universe in an infinite ensemble, because the mathematics of probability does not extend coherently into infinite sets without additional assumptions, and those assumptions are themselves contested and ungrounded. The multiverse was invented to make our universe's fine-tuning statistically unsurprising. But in the mathematical framework required for the multiverse to be infinite, statistical reasoning stops working. The solution undermines its own logic. The second problem is more intimate, more personal. And this is the part that most popular accounts of the multiverse skip entirely, because when you follow it to its conclusion, it says something about you specifically that is profoundly difficult to sit with. If the multiverse is real, if there are infinite universes with infinite variations, then it is not merely your universe's physics that varies across the ensemble. Everything varies. Every possible configuration of matter and energy, every possible history, every possible sequence of events is realized somewhere in the infinite space of possibilities, which means that somewhere in the multiverse, every version of you exists. Every choice you didn't make was made. Every path you didn't take was taken. Every thought you suppressed was expressed by a version of you in a universe indistinguishable from this one up until the moment of divergence. But it goes further than that. In an infinite multiverse, the overwhelming majority of observers, the vast majority of conscious beings across all universes, did not arise through the slow, structured process of biological evolution on a stable planet orbiting a stable star. They arose as random quantum fluctuations, as temporary, momentary condensations of order in an otherwise entropic void, what physicists call Boltzmann brains, entities that flicker into existence with false memories of a life they never lived, in a universe that doesn't actually have the structure they seem to remember, and disappear again in an instant. In an infinite multiverse, you are almost certainly a Boltzmann brain. The probability that you are a genuinely evolved biological consciousness with an accurate memory of a real past, in a real universe with the structure you think it has, is vanishingly small compared to the probability that you are a momentary fluctuation with false memories. Which means that if the multiverse is true, you have no rational basis for trusting your own perception of reality. Your memories, your senses, your scientific instruments, your entire framework for evaluating evidence, all of it becomes suspect. The multiverse, taken seriously to its logical conclusion, dissolves the epistemic ground that science itself stands on. This is not a reductio ad absurdum invented by critics. It is a recognized problem within the field, discussed seriously by physicists, including Sean Carroll and others who are genuinely sympathetic to multiverse cosmology. The framework has consequences that the framework cannot escape from. And one of those consequences is that it potentially undermines the very capacity for rational investigation that led physicists to construct it in the first place. There is a third problem, quieter and more structural. It concerns what the multiverse actually requires at the level of initial conditions. The most developed framework for generating a multiverse, eternal inflation, requires an inflaton field with specific properties, a potential energy landscape of a particular shape, a set of quantum fluctuation mechanisms operating within defined parameters. In other words, it requires physics. It requires laws. It requires a framework that is itself structured in a very particular way. The multiverse doesn't generate itself from nothing. It generates itself from a prior physical setup that is, and here the recursion becomes nauseating, itself potentially fine-tuned for universe generation. You have not escaped fine-tuning. You have embedded it in a higher level structure and declared the problem solved. George Ellis, one of the most respected relativists in the world and a longtime collaborator of Stephen Hawking, has been explicit about this. The multiverse, he argues, is not science in any meaningful sense. It is a philosophical preference dressed in the language of physics, used to avoid a conclusion that some physicists find philosophically unacceptable. It is not that the multiverse is certainly wrong. It is that the multiverse is certainly untestable, and in that untestability, it occupies exactly the same epistemological territory as the alternatives it was designed to exclude. So here is where we stand. We have now eliminated every comfortable answer available within the standard naturalistic framework. Fine-tuning is real. Physicists agree on this. The anthropic principle does not explain it. It requires the multiverse to function. The multiverse cannot be tested, generates its own fine-tuning problems, and taken to its logical conclusion undermines the rationality of the observer invoking it. Every exit leads to a wall. Every solution introduces a problem larger than the one it solved. Both paths that remain, a designed universe or an infinite random multiverse, require accepting something that cannot be empirically verified. Both require a form of commitment that goes beyond what the data alone can compel. The question is no longer which answer is scientific. The question is which extraordinary claim you find less terrifying. And we haven't even reached the strangest part yet, because it isn't only the numbers that look designed. It isn't only the constants, the calibration, the improbable precision sitting at the foundation of physical law. It's something else, something that cuts even deeper. Because it isn't about what the universe contains. It's about what the universe is made of at the most fundamental level, not matter, not energy, not force. Language, structure, logic, mathematics, the universe is not merely described by mathematics. Physicists have found something far more unsettling than that. And it is waiting in the next layer down. In 1960, a physicist named Eugene Wigner wrote a paper that should have caused a crisis. It didn't, not immediately, not loudly, but the question it asked has been quietly destabilizing the foundations of scientific thought ever since, surfacing in the private conversations of mathematicians and physicists who are willing to follow the logic wherever it leads. The paper was called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The title sounds academic. The content is, if you take it seriously, one of the most unsettling things ever written by a scientist about science. Wigner's observation was simple. Mathematics, abstract, formal, invented by human minds working in isolation from physical reality. Developed according to internal rules of consistency and elegance with no requirement to correspond to anything in the external world, keeps describing that external world with perfect, almost embarrassing accuracy. Not approximately, not loosely, with a precision that has no business existing if mathematics is simply a tool that humans constructed for practical purposes. This should strike you as strange. It doesn't, usually, because we are so accustomed to the fact that physics uses math that we have stopped noticing how extraordinary that fact is. But strip away the familiarity for a moment and look at what is actually happening. A human being sits in a room, using only thought, no experiment, no instrument, no observation of the physical world. That human develops a system of abstract relationships between quantities that exist nowhere in nature. Numbers are not physical objects. Equations are not forces. Geometric structures are not matter. They are patterns of pure logic, existing only in the conceptual space of a mind working through abstract relationships. And then, when physicists go out and measure the actual behavior of actual physical reality at scales ranging from the subatomic to the cosmological, they find that reality is already obeying the mathematics. Not approximately, not as a rough guide. The universe is running on the equations. Consider what this means in practice. James Clerk Maxwell developed his equations of electromagnetism in the 1860s as a purely theoretical framework, a set of mathematical relationships that unified what was known about electric and magnetic phenomena. Embedded in those equations as a pure mathematical consequence was a prediction that oscillating electric and magnetic fields would propagate through space as a wave, and that the speed of that wave would be approximately 300,000 kilometers per second. Maxwell had not measured this. He had not designed an experiment. He had followed the mathematics. And what he found, sitting inside the algebra, was light. The mathematics predicted the existence and speed of electromagnetic radiation before anyone had looked for it. The universe had already been running on Maxwell's equations before Maxwell wrote them down. This pattern repeats throughout the history of physics with a regularity that should feel more shocking than it does. Paul Dirac, working in the late 1920s on the mathematical formalism of quantum mechanics, produced an equation describing the behavior of electrons that was internally consistent and mathematically elegant. The equation had two solutions. One described the electron as observed. The other described a particle identical to the electron but with opposite charge. A particle that had never been observed, that nobody had predicted from experiment, that had no empirical basis whatsoever at the time Dirac wrote the equation. Dirac followed the mathematics and found antimatter. 2 years later, the positron was discovered in a laboratory. It was exactly where the equation said it would be. General relativity predicted black holes before anyone believed they could exist. It predicted gravitational waves a century before we had instruments sensitive enough to detect them. Quantum field theory predicted the existence of the Higgs boson using mathematical symmetry arguments decades before any accelerator was powerful enough to produce one. In each case, the pattern is identical. Humans write equations, follow the internal logic of the mathematics, and find that reality has already arranged itself in accordance with what the math implies. The universe is not merely compatible with mathematics. It appears to be running the mathematics as its source code. Eugene Wigner found this unreasonable. And he was right to, because if mathematics is a human invention, a conceptual tool we developed to organize quantities, initially to count livestock and measure land, later to describe motion and force and eventually quantum fields, then there is no obvious reason why it should describe reality at all, let alone describe it perfectly at scales and domains that had nothing to do with the contexts in which any of the Mathematics was developed. The mathematics of differential geometry was invented by Bernhard Riemann in the 1850s as a pure exercise in abstract reasoning about curved spaces. Einstein picked it up 60 years later and used it to describe the curvature of spacetime. Riemann was not thinking about gravity. He was not thinking about the universe. He was following the internal logic of geometry into abstract spaces that had no known physical correspondent. And yet the physical correspondent was waiting. The universe had been curving according to Riemannian geometry for 14 billion years before Riemann was born. This is the puzzle. This is the thing that Wigner pointed at, and that the scientific community has largely decided to call mysterious and then continue working. But calling it mysterious does not dissolve the problem. It merely assigns it a category and moves on. The question itself remains, and it is not a small question. Why does abstract mathematics describe physical reality? There are a limited number of possible answers. The first is that mathematics is genuinely just a tool, that it is flexible and general enough that given enough mathematical structures to choose from, some of them will happen to fit whatever physical reality we observe, and we simply discard the ones that don't match. This is the pragmatist's answer. It sounds reasonable. It collapses under scrutiny. Because the mathematics that describes physics is not selected from a vast menu after the fact, in case after case, the mathematics came first. It was developed independently, followed to its logical conclusions, and then found to match physical reality with extraordinary precision in domains that had not yet been explored experimentally. That is not curve fitting. That is prediction, and the predictive success of pure mathematics applied to physics is not occasional or marginal. It is the central methodology of the field. It is how physics actually works. The second answer is Platonic. Mathematics is not invented. It is discovered. Mathematical structures, numbers, equations, geometric forms, topological relationships exist independently of human minds, as abstract objects in some non-physical realm of pure structure. When mathematicians do mathematics, they are not constructing new things. They are exploring a pre-existing landscape of mathematical truth that would be exactly what it is even if no mind had ever contemplated it. And physical reality obeys mathematics because physical reality is made of mathematical structure. The universe is not described by math. The universe is math, a particular region of the space of mathematical structures instantiated as physical existence. This is not a fringe position. Max Tegmark, a cosmologist at MIT, has developed it into a rigorous theoretical framework called the mathematical universe hypothesis. His argument is precise. If physical reality is a mathematical structure, then the unreasonable effectiveness of mathematics is not mysterious at all. Mathematics describes the universe perfectly because the universe is mathematics. The mystery dissolves. But what replaces it is something that requires you to fundamentally revise what you think exists. Matter is not fundamental. Energy is not fundamental. At the deepest level, what is real is structure, abstract, mathematical, formal structure, and what we call the physical world is what that structure feels like from the inside. The universe is not a physical accident that happens to be describable in mathematical language. The universe is the mathematical language, running itself. If that is true, then several things follow that are genuinely difficult to absorb. First, the universe did not need a physical substrate to begin. Mathematical structures do not require physical instantiation to be real in the Platonic sense, which raises the question of why this particular mathematical structure exists as a physical universe rather than remaining as abstract structure. And that question does not have an answer within the framework. Second, the constants that appeared fine-tuned in earlier sections are not arbitrary numbers embedded in physical law. They are specific parameters of a specific mathematical structure, which makes the fine-tuning question not a question about physics, but a question about mathematics, about why this mathematical structure has these parameters rather than others. And that is a question that goes somewhere no current framework can follow. Third, and this is the one that produces genuine vertigo, if the universe is a mathematical structure, then the boundary between abstract existence and physical existence is not what you thought it was. Things that exist mathematically, formally, consistently as self-contained structures may exist in the same sense that the universe exists. Every consistent mathematical structure might be real in exactly the way our universe is real. And you are somewhere inside a specific one, made of atoms obeying equations, equipped with a brain that can reconstruct the equations from observation and then use those equations to explore the structure you're embedded in. You are a biological creature. You are made of carbon and hydrogen and oxygen, assembled by 4 billion years of undirected chemical evolution into a system of approximately 100 trillion cells. Sitting on a rock orbiting a medium-sized star in an unremarkable corner of one galaxy among hundreds of billions. And somehow, through processes that are themselves not fully understood, you can write equations on a piece of paper that accurately predict the behavior of objects 13 billion light-years away, at the edge of the observable universe, in conditions that no human being has ever directly experienced and no instrument has ever directly reached. Equations that describe what happens inside black holes. Equations that predict the mass of particles before they are discovered. Equations that extend your perception across scales and domains that your senses were never designed to access. That is not normal. That is not what you would expect from a biological organism that evolved to find food and avoid predators on the African savanna. That is not what the process of natural selection, optimizing for survival in a local environment, would be expected to produce. The ability to do theoretical physics, to reason about the abstract structure of reality at cosmological and quantum scales using pure mathematics, is not obviously an adaptive trait. It is an ability that wildly exceeds anything that evolutionary pressure alone would seem to require. Either that capacity is a spectacular accident, or the structure of the universe and the structure of the mind capable of understanding it are not as separate as they appear. That question does not have an answer yet, but it gets stranger, because we have been treating the mind as a tool for investigating the universe. What if that framing is backwards? What if the universe and the mind capable of perceiving it are not two separate things, one physical, one biological, but aspects of a single structure? What if consciousness is not something the universe produced by accident, but something the universe cannot be fully described without? That is where we are going next. And nothing that comes after will feel like solid ground. Here is where physics stops being physics and starts being something else entirely. Everything we have covered so far has operated within a framework you could, with effort, hold at a distance. The fine-tuning of constants, the failure of the anthropic principle, the philosophical bankruptcy of the multiverse, the unreasonable effectiveness of mathematics, these are unsettling. But they are unsettling in the way that a very difficult puzzle is unsettling. There is still a you standing outside the problem looking at it. There is still a solid floor beneath your feet. There is still a clear boundary between the observer and the observed, between the mind investigating reality and the reality being investigated. That boundary is about to disappear. What follows is not philosophy. It is not religion. It is not speculation dressed in scientific language to make it sound more credible than it is. What follows is the direct, unambiguous implication of the most precisely tested theory in the history of science. A theory whose predictions have been confirmed to more decimal places than any other framework humans have ever constructed. It is peer-reviewed. It is mathematically rigorous. It has been debated by Nobel Prize winners for 80 years. And it has not been resolved. Not provisionally. Not approximately. Not resolved at all. The theory is quantum mechanics. And what it says about the nature of reality, when you follow it without flinching to its logical conclusion, is this: the universe, at its most fundamental level, does not fully exist until it is observed. To understand why that statement is not metaphorical, you need to understand what quantum mechanics actually describes. At the quantum scale, the scale of electrons, photons, quarks, and the fundamental interactions between them, physical systems do not have definite properties until those properties are measured. An electron does not have a specific position. It has a probability distribution of possible positions, a wave function that describes the likelihood of finding it in any particular location if you were to look. Before you look, the electron is not in any single place. It is, in a precise mathematical sense, in a superposition of all possible places simultaneously, each weighted by its probability amplitude. This is not a limitation of our knowledge. It is not that the electron has a definite position and we simply don't know what it is. The mathematics of quantum mechanics, confirmed by experiment after experiment across a century of increasingly precise testing, describes a reality in which definite properties genuinely do not exist prior to measurement. The wave function is not a map of our ignorance. It is a map of what is actually there. And what is actually there before observation is not a particle with a location. It is a smeared probability, a superposition, a quantum of pure potential. Then something happens. Someone or something interacts with the system in a way that constitutes a measurement, and the wave function collapses. The superposition resolves. The probability distribution reduces to a single outcome. The electron is now somewhere specific. Reality at that location has become definite. This process, the collapse of the wave function upon measurement, is called the observer effect. And it is where quantum mechanics becomes genuinely difficult to look at directly, because the question it raises is one that the mathematics itself does not answer. What counts as an observation? This is not a peripheral question. It is the central interpretive problem of quantum mechanics, and it has been unresolved since the theory was first formulated in the 1920s. The equation that describes the evolution of a quantum system, the Schrödinger equation, is perfectly deterministic. It describes a wave function evolving smoothly and continuously through time. But that smooth, deterministic evolution does not produce collapse. Collapse is something different. It is discontinuous. It is irreversible. It selects one outcome from the superposition and discards all others. And the Schrödinger equation does not tell you when or why it happens. It does not tell you what triggers it. It does not tell you what the difference is between a quantum system evolving in superposition and a quantum system collapsing into a definite state. The Copenhagen interpretation, the standard textbook answer, says that collapse happens when a measurement is made by a classical observer. But this simply relocates the problem. What is a classical observer? At what scale does quantum behavior give way to classical behavior? Where exactly is the boundary between the quantum world of superpositions and the classical world of definite things? The Copenhagen interpretation does not answer these questions. It draws a line and says, on this side, quantum mechanics, on that side, classical reality. Do not ask what the line is made of. John von Neumann, one of the most rigorous mathematical minds of the 20th century, followed the logic of quantum mechanics further than most were willing to go. His analysis produced something that the physics community has been quietly uncomfortable with ever since. Von Neumann showed that if you apply quantum mechanics consistently, if you don't draw an arbitrary line between quantum and classical, but instead treat every physical system, including the measuring apparatus, as a quantum system governed by the same equations, then the collapse of the wave function is never produced by any physical interaction alone. Physical interactions simply entangle systems into larger superpositions. The measuring device becomes part of the superposition. The laboratory becomes part of the superposition. Everything physical that interacts with the quantum system simply joins the spreading web of quantum uncertainty. The only thing that is not physical, the only thing that sits outside the chain of entanglement, is the conscious observer registering the result. Von Neumann's mathematics pointed directly at consciousness as the termination point of the measurement chain, not as a philosophical preference, as a mathematical consequence. This conclusion was so uncomfortable that most physicists declined to accept it, preferring instead to develop alternative interpretations that avoid the implication. The many worlds interpretation says wave functions never collapse. Every possible outcome is realized in a branching multiverse of parallel realities. Decoherence theory says that quantum superpositions become practically indistinguishable from classical mixtures when they interact with large environments, which explains why we don't see quantum behavior at macroscopic scales, but notably does not explain why any single outcome is experienced rather than all of them simultaneously. Each interpretation sidesteps the observer problem in a different direction. None of them resolves it. And John Wheeler, who named the black hole, worked alongside Einstein and Bohr and spent 60 years at the absolute frontier of theoretical physics, chose in the final decades of his life to look at the problem directly rather than around it. Wheeler developed what he called the participatory universe. His argument was not mystical. It was grounded in the mathematics of quantum mechanics and in a series of thought experiments, some of which were later realized as actual experiments that produced results even more disorienting than the basic observer effect. The most famous is the delayed choice experiment. In a standard double-slit experiment, a particle fired at a barrier with two slits will produce an interference pattern on a detector screen, the signature of wave behavior, of something passing through both slits simultaneously and interfering with itself. But if you add a detector to determine which slit the particle actually passed through, the interference pattern disappears. The particle behaves as a particle, not a wave. The act of observation changes the outcome. Wheeler asked, "What if you delay the choice of whether to observe which path the particle took until after the particle has already passed through the slits?" This is not a thought experiment anymore. It has been performed in multiple laboratories, with light and with atoms, with the choice delayed by distances and time intervals that make classical explanation impossible. The result is consistent and deeply strange. The choice of whether to observe the path of the particle, made after the particle has already passed through the apparatus, determines what the particle was doing in the past. The future measurement reaches backward in time and changes the prior behavior of the system. Wheeler's conclusion was precise. The universe is not a machine that runs independently of observation, with observers passively watching from the sidelines. Observers, conscious, information-registering systems participate in bringing reality into definite existence. The universe, at the quantum level, is not fully real in the absence of observation. And observation, in Wheeler's framework, is not incidental to the universe's existence. It is constitutive of it. Now hold this next to everything that came before. The universe's fundamental constants are calibrated with extraordinary precision to permit the existence of life. Life, after billions of years of development, produces conscious observers. Entities capable of registering information, making measurements, collapsing quantum superpositions into definite outcomes. And those observers, according to quantum mechanics, are required to make reality fully real. Not metaphorically, not philosophically, operationally, in the mathematical structure of the most tested theory in science. The universe was fine-tuned for life. Life was required to produce observers. Observers are required, in some interpretation of quantum mechanics, to collapse probability into actuality, to participate in the completion of physical reality, which means the universe needed life in order to fully exist. And life needed the universe to be fine-tuned in order to exist at all. The loop has no beginning. The universe requires observers to be real, and observers require a fine-tuned universe to exist. Cause and effect have turned back on themselves. The universe is not a stage on which life performs. Life is not an accident that the universe produced. They are bound together in a relationship of mutual necessity that no causal framework currently available can fully untangle. Wheeler spent decades on this. He called it the most important question in physics. He called the universe a self-excited circuit, a system that bootstraps its own existence through the act of observation, that reaches back through time via the choices of its observers to participate in its own creation. He developed diagrams, a universe shaped like the letter U, with the observer at one end reaching back to observe the Big Bang at the other, completing a loop of participation that gives the cosmos its definiteness. He died in 2008 without a resolution. The question he spent his life on is exactly as open today as it was when he first formulated it. And here is what that means, not abstractly, but for you, specifically, sitting where you are right now. The atoms in your body were forged in stellar interiors over billions of years, in a universe calibrated to allow stellar fusion at the precision of a single part in 1,000 trillion. The carbon in your cells required a nuclear resonance so exact that Fred Hoyle, an atheist, said it looked like something had monkeyed with physics. Your existence required every one of the 6 constants to be exactly what it is. Your brain, running electrochemical processes that are themselves quantum mechanical at their base, is the product of 4 billion years of complexity building in a universe that had no obvious reason to permit complexity at all. And when you observe the world around you, when light strikes your retina and your visual cortex collapses the quantum probability distribution of photons into the definite image of a room, a screen, a face, you are not passively receiving information about a pre-existing reality. You are, in some sense that physicists have not yet fully agreed on, participating in the completion of that reality. You are the universe observing itself, and in that observation, something that was indefinite becomes definite. Something that was potential becomes actual. The universe needed something like you to exist. The question is whether that need was accidental or whether it was written in from the beginning. That question belongs to you now. And it isn't an abstraction. It is not a puzzle you can leave on the page and walk away from. It is a question about what you are, why you are here, and what your existence means within a cosmos that appears, at every layer of investigation, to have been arranged with your eventual arrival in mind. Everything has been stripped away. Every comfortable answer has been examined and found hollow. The floor is gone. What remains is not an answer. What remains is something more unsettling and more personal than anything a scientific framework can contain. And that is exactly where we are going next. Stop for a moment. Not metaphorically. Actually stop. You have spent this entire video watching an argument build, layer by layer, constant by constant, equation by equation, toward something that science refuses to name. You have watched the comfortable answers dissolve. You have watched the escape routes close. You have watched physicists of extraordinary intelligence and integrity circle a conclusion they cannot bring themselves to state directly. And you have processed all of it probably as information, as content, as something happening out there in the abstract space where cosmology and philosophy meet, fascinating and disturbing in the way that very large ideas are disturbing. At a safe distance, behind the glass of intellectual curiosity. That distance is about to close, because here is what we have not yet said directly, even though it has been implicit in every section, hiding inside every equation, present in the silence between every argument. Here is the thing that the scientific framing tends to obscure, that the careful language of peer-reviewed physics tends to bury under abstraction, that the responsible reluctance to draw metaphysical conclusions tends to leave permanently unstated. All of it, every constant, every calibration, every number sitting at the precise edge between existence and annihilation, was necessary for one thing. Not for stars, not for galaxies, not for chemistry or biology or complexity in the abstract. Those are intermediate steps. Those are the mechanism. The thing that required the universe to be configured with a precision of 1 part in 10 to the power of 60, the thing that required carbon's nuclear resonance to thread an impossibly narrow window, the thing that required omega to be balanced to 1 part in 1,000 trillion in the first second of existence, the destination of all that calibration, the output of 14 billion years of structured cosmic development, is you, sitting here, aware, asking the question. You are not an observer of the fine-tuning. You are the fine-tuning's product, its terminus, the event toward which an improbably calibrated universe appears, from the inside, to have been building. Science tells you something very specific about your place in this cosmos. It tells you that you are an accident, a local, temporary, vanishingly improbable fluctuation of order in a universe trending toward entropy. It tells you that the atoms in your body do not know they are in a body, that the universe does not know you exist, that consciousness is a late and incidental product of physical processes that were never aiming at anything, that you are not the point. You were never the point. The universe was not arranged with you in mind, and the feeling that it might have been is a cognitive bias, a pattern-seeking error produced by a brain that evolved to find agency in random events because mistaking wind for a predator was cheaper than the alternative. This is the official position. It is taught in universities. It is assumed in laboratories. It is the operating premise of every naturalistic account of human existence currently on offer. And yet, everything we have examined today pulls in precisely the opposite direction. Not because someone is arguing for it. Not because a philosophical tradition demands it. Because the physics itself, followed without flinching to its furthest implications, keeps arriving at the same disturbing address. The constants are calibrated for life, not accidentally life permitting, calibrated precisely to the degree required for biology, chemistry, and consciousness to emerge. The mathematics that describes reality is the same mathematics that your mind generates independently and then finds encoded in nature, as though the universe and the capacity to understand it were built from the same source. The quantum structure of reality requires observers to collapse probability into actuality, which means that the universe at its most fundamental level is not complete without something like you looking at it. And Wheeler's participatory universe places the conscious observer not at the periphery of cosmic history, but at its functional center, the thing the self-excited circuit requires in order to close the loop and become real. These are not religious claims. They are not arguments from tradition or authority or feeling. They are the logical consequences of the best physics we have. And they converge on a conclusion that is almost impossible to hold in your mind without something shifting, some quiet tectonic movement in the way you understand what you are. You are not an accident that became aware. You are the universe becoming aware of itself. You are the mechanism by which 14 billion years of structured physical development looks back at its own beginning and asks why it happened. And that act, the act of asking, may not be incidental to the universe's existence. It may be, in some sense, that current physics cannot fully formalize, constitutive of it. Feel what that means. Not intellectually. Feel it. Every photon that has ever struck your retina was produced by nuclear fusion in a star, in a universe calibrated to permit stellar fusion at a precision that has no known physical explanation. Every thought you have ever had was generated by electrochemical processes in a brain assembled from atoms forged in stellar interiors and scattered across space by supernova explosions. Explosions that required the electromagnetic force to be exactly what it is, the gravitational constant to sit exactly where it sits, the cosmological constant to be almost precisely zero rather than the enormous value quantum field theory predicts. Every memory you carry, every perception you have ever experienced, every moment of consciousness that has constituted your life, all of it required the universe to be configured, from its first second, in a way that had no logical necessity and no known physical cause. The universe did not have to permit you. By every calculation, by every assessment of prior probability, by every theoretical framework that attempts to account for the values of the fundamental constants, it shouldn't have. The space of possible universes is effectively infinite. The fraction of that space that permits stars, chemistry, biology, and consciousness is so small that the word small fails it. And yet here you are, in one of the universes that made it through every filter. In a universe that not only permits your existence, but, if the participatory framework is even partially correct, may require it. The question you now have to sit with is not abstract. It is not safely located in the domain of physics or philosophy or cosmology, where you can appreciate it and then set it down when the video ends. The question is about you, about what it means to be the kind of thing you are, a conscious, observing, questioning entity, in a universe that appears to have been built for exactly that. There are two ways to hold everything we have covered. You can hold it lightly, as a collection of fascinating puzzles at the frontier of science, filed under interesting unsolved problems, appreciated for the intellectual texture, and then returned to the shelf. Many people do this. It is the safe choice. It is also, if you have been paying attention, increasingly difficult to sustain. Because the puzzles don't stay on the shelf. The questions follow you. The numbers don't stop being what they are when you stop thinking about them. The loop between observer and universe doesn't close just because you chose not to look at it. Or you can hold it the other way. You can let the full weight of it land. You can accept that you are standing at the intersection of the most profound unresolved questions in science, fine-tuning, mathematical structure, quantum observation, participatory reality, and that you are not just a spectator at that intersection, but a constituent of it, that your existence is not a footnote to cosmic history, but the event that, in Wheeler's framing, the universe has been building toward and requires in order to complete itself. Neither option is comfortable. That is not an accident. The universe we actually inhabit, the one the physics describes, does not appear to be designed for comfort. It appears to be designed for something more difficult and more extraordinary than that. It appears to be designed for awareness, for the specific, terrible, vertiginous experience of a conscious being looking outward at a cosmos it did not create and recognizing, against every instinct of intellectual modesty, that it is somehow central to the story. You have been told your entire life by the most authoritative voices in science and culture that you are small, that the universe is vast and old and indifferent, and that you are a brief, local, fragile improbability somewhere near the edge of an unremarkable galaxy. You have been told that the feeling of significance is a cognitive error, that the intuition that you matter, that your existence is not random, that the universe is not indifferent to you, is a bias to be corrected, not an insight to be followed. Every piece of physics we examine today suggests that story is, at minimum, incomplete, and at the maximum implied by the constants, the mathematics, the quantum structure, and the participatory framework taken together, it may be precisely backwards. We do not know if the universe was designed. That is the honest statement. No equation proves it. No observation confirms it. No experiment can reach the question directly. The most rigorous minds in the history of science have circled it for a century without resolution. The silence at the center of the question is real, and it would be dishonest to fill it with certainty that the evidence does not support. But we know something else. Something that the evidence does support unambiguously at every scale and in every domain we have examined. We know what the universe looks like. It looks designed. It looks calibrated. It looks encoded. It looks as though the constants were chosen, the mathematics was embedded, the quantum structure was arranged, and the whole 14 billion year unfolding was oriented toward the production of something that could look back at it and ask why. It looks, with a precision and consistency that no comfortable explanation has yet dissolved, exactly as though you were always the point. We don't know if the universe was designed, but we know this. It looks exactly like it was. And the difference between those two statements is everything.